Okay, we're gonna continue watching a little bit more of Ahmad's podcast and see what he can teach us. So with that, let me gonna roll him back a little bit here. I think that's probably pretty good. Yeah. Okay. Super. So here we go. Let's learn some more from Ahmad, and we'll see if we can get him to have me not interrupt him for more than 30 seconds. I'm sorry, Ahmad. You have so many amazing things to say that I somehow can't contain myself. So, yeah. It's like we're working together already. This is, as the Merlians and the university folks will probably tell you, this is, it's a bad habit that I have, but I mostly reserve it for people that I am deeply interested in because I become hyper engaged in the things that they're saying. So it's the highest form of compliment I can give anyone, I guess is what I'm trying to say. All right. So now, Ahmad, back to you.
Or fix errors to address vulnerability. As suggested in Figure 1, intention, emission, and adaptation. Figure 1 is here. Excuse me. I feel like right now we're still very much struggling with just the intention part. And until we figure that out, I mean, this is going to require investing. It's not just the machine. Like we will need to build platforms where programmers themselves actually put in the time to index, to actually look at data and catalog it, catalog code snippets and all that. Basically, code curation, but except in that case, code is actually data, so it's really a data curation thing that is co-piloted by AI. Like just looking, I mean, if you wanted to just even look at the ClickHouse C++ code base, I'm sure that there's so much code in there that I think we can be labeled as interesting, right? But to so many people, it's not accessible, right?
Yep.
Like, and it's not necessarily that they don't have the capacity to understand what the code is doing. It's just that the code itself is getting in the way, right?
Yeah, and it's tricky because, at least from my perspective, if the software is designed in the right way with the right kinds of abstractions, then the code can be understandable, I think, by even people that are not expert coders. And kind of what I'm hinting at here is there's certain techniques that Uncle Bob, Robert Martin, if I'm recalling correctly, from Clean Code, talks about with same level of abstractions for methods or functions. And I've definitely seen what you're talking about, Ahmad, that the code can get in the way of understanding what is being done, especially when the abstraction levels are sort of intermixed in the same scope. And by scope here, let's just say it's function or method or something of that nature. And of course, it can be scope inside of scope, all of this. By the way, just as an aside, since we're talking about code, I'm a huge fan of never nesting. In fact, in my production code, I strive for never having more than 2 levels of nesting. And if I go beyond 2 levels, I almost always refactor it right away. And a big reason for that is I think that's an example of varying degrees of abstraction. I strive for only 1 level of scope. So you have like the method, and it just kind of reads like a serial set of instructions. Even if it contains conditions that, again, if you designed it, I think maybe the right way, you can, there's a bunch of philosophies that I try to follow, but one of them is you deal with all the unusual cases first. So any method that's meant to do something, the first thing you do is you deal with all the things that could go wrong that would prevent you from doing the thing. And the reason why you do this first is, one, this is my view, those unusual cases tend to actually be the majority of the work. The correct case is the easy case. And I think this is sort of like the difference between novice programmers and expert programmers. The novices will often think about just the correct case, and then they will miss all kinds of errors. Whereas the expert programmers will literally start and iterate through exhaustively all of the error cases, and they'll handle all those first. And then, when all of that's handled, the only thing that's left is the correct case. And that is extremely simple. So then what happens is, for any method that's doing something, you sort of have 2 blocks. You have the things go wrong block, and usually you exit, or the I can do the actual thing. And what's nice about dealing with all the things that can go wrong stuff first, those cases usually require you to exit, because you can't continue to do the bad stuff. Sorry, you can't continue to do the good stuff because you're in like a bad state. But if you try to check for all the good stuff first, then you have to go in an embedded scope to deal with all the things that are required to go right to deal with this. And then that means that after that, you have to deal potentially in another scope all the stuff that could potentially go wrong that you didn't handle in this case. So you have extra scope that creeps in. It's usually in the form of a big if and then an else. And then if it's really bad, it's things like if, and it goes do, and it just becomes a nightmare. But if you invert it and do the error cases first, you check for the highest order error. Oh, you have it, you exit. Oh, you don't have it, you can check for the next depth, but you don't need to embed them, because you know that if you didn't exit from the first thing, you can go into the next thing. So it's sort of like if you had a chain of objects that you're referencing, or a chain of pointers, you check to see if the first pointer is null. It's not? Okay, now I can check to see if the second pointer is null. It's not, and continue. And so each time you're doing, if this pointer is null, oh, it is, exit. If this other next pointer is null, exit. And so each of them is sequentially getting more complex, but they all stay at the same level of scope. the highest order of scope. And then when you get done with all those cases, you don't even need an embedded level of scope, because all the bad cases would have already exited that method at that point. And so if your thread of execution didn't exit, it means you're in the good state. And so you can just execute the code serially. Then, on top of that, all of the code that checks for all the error states can be made a single function. Like, does it pass or is in invalid state? If it is, return. And then all that complexity is its own method. And now the new method is invalid state, exit. Otherwise, it's in a good state, and do the good stuff. And what I find is that most people can reason about that very easily, even if they aren't expert coders, even if they don't understand programming language syntax, because it's designed in a way that essentially reads almost like a sequence of events. It's like asking someone to drive to the grocery store, and they are checking, oh, do I have all the stuff I need to go to the grocery store? Oh, I don't? I guess I can't go. Or, oh, I do? Okay, go to the grocery store. So, going back to your point, Ahmad, I think, and by the way, this is supremely hard, in my opinion. Writing code like this requires a huge degree of expertise, I think, and a level of sort of incredible care for proper software development to make things as simple as possible so they can be highly extensible. And I know a few coders that can do this, but the reason why this is so important to me, and what I try to do is do this for all my production quality code, is that it tends to make maintenance and extensibility of those software systems significantly easier. That all the code, I think Donald Knuth has this saying, I think it was Don that said it, and it goes something like this. There's two ways to write code. One, where there are no obvious bugs, or two, where there are obviously no bugs. The second is significantly harder. So one more time. There's two ways to write code. One, where there are no obvious bugs, or two, there are obviously no bugs. The second is significantly harder, and I absolutely agree with that. I think writing code so it's so clear that it must be right requires master level software development skills, master level ability to create. This is like the art of software engineering. This is like, you have to, I think, really, really care and consider code like it's your own personal masterpiece. Like you are the lead singer of the band, and this is your art. And interestingly enough, I think that a lot of the true sort of coding savants that I know, this is exactly how they feel about their code. So, for example, some of the folks at Merle, Taylor Dozel, Tim Mattson, and my co-founder and chief engineer and architect, Urs Muff. All three of those guys, I know, think of code like this. It is a reflection of themselves. It's not code that like does something. It is their art. It's their work. It's an extension of themselves. And so it has this extreme level of care and attention that it really bothers them if the code is not something they would be proud of. Or maybe proud's the wrong word, but something they would feel ashamed of. And again, we're a small startup and we have to move really fast. And the person that comes the most to mind here is Urs. Urs has to, he's almost single-handedly coded Mentor himself. That mostly sort of the way that Merly works is I have these insane ideas and it makes sense in my head because I'll walk through basically all the logic and I can put it all together and I think, yeah, this is going to work. And then, at least this is how it was historically. I mean, we have many engineers working on things now. But again, Urs is, I'm just going to tell it straight here. Urs is a one-off. Urs is, he's like not human in what he can do. Truthfully, I mean, we had one of my students from the university recently join Merly, and I was talking to him, I was asking him what his experience is like being at Merly, and he's saying, oh, it's really interesting working with all these smart people. And he said, but I was looking at the commits and I was noticing the work that Urs is doing, and he was saying, I've never seen something like this before. Like, it doesn't even make sense that this person could be writing this much high quality code. And, I said, yeah, well, it can, and it does, because clearly you've seen the evidence of it. But yeah, this is why he's my chief engineer and a chief architect. So that he knows what he's doing. And he's arguably one of the best in the world, literally, which I don't say lightly, and I'm going on public record here saying this, and it stands the test of time. I've known Urs for, 25 years, and he was a superstar 25 years ago, and he's just gotten better with time. Although he and I will joke about, we're not sure how many more years our brains are going to work, and so we really need to keep chugging along, because I think we're both in our 50s now, and yeah, I don't know, there's some belief that 65 is, I don't know, I think Jeff Hinton it's like almost 80, or maybe he's in his 80s, and he seems to be firing all cylinders. So whatever it is, I think we can go beyond 65. That's my hope anyway, fingers crossed. But anyway, the point I'm trying to make here, that I got massively sidetracked, is I'm with you, Ahmad. I think that there's a number of really interesting things to observe in software, and oftentimes the code can get in the way of that, and it kind of breaks my heart a little bit when I see this, especially when it could be resolved if people took a little more care for really leaning in to write things that are easy to understand, that are highly modular, that are that make a lot of sense in terms of the way that they're loosely coupled but strongly cohesive, which I think is maybe one of the goals or one of the things that they talk about in the Gang of Four design patterns book. I think it's somewhere out there. Maybe Scott Myers in one of the C++ books. I'm not sure. But I think that that's absolutely true, and we should work toward code that, as I suspect many of us have heard, this code that's so brilliant that it's self-documenting. And I do think that you can write code that is essentially self-documenting, that the code itself explains what it's doing. Although still, I think for highly complex code, maybe in the next episode I'll show the DOTSA system that I built that is a data synthesizer. And it's used for machine learning systems where it's basically synthesizing data that is pseudo-random, but it's controlled based on parameters that you provide it. And it's used essentially to help accelerate the training of machine learning and machine programming systems. That's sort of like the intention behind the DOTSA system. Anyway, in the DOTSA system, because it's designed to be highly extensible, there's like I think that there is one member in one of the base classes that I think might even be commented out, but it's still in the code. And I have like a 2-paragraph explanation of this variable that doesn't exist and why it's so important. I'll see if I can find it for the next podcast. But the point is that even for someone like me that is trying really, really hard to make the code super readable, there are cases, I think, that exist where we still get into complicated code that requires us to document things, that requires some comments. Now, admittedly, most of the code that I write, it's comment-free. I'll put like these separator blocks just to do mental separation of concepts, but then the separation blocks won't even include, like I'll put the separation blocks maybe at the beginning of functions, but then I won't even include anything about what the function does, because it's so clear from the function name and the code that adding a comment would be more work, essentially, not just for me that's writing the code, but also for people that are reading the code. And then of course you get the code comment drift, right? This is one of the big dangers, is that code is maintained oftentimes because it must be, in order to ensure that the behavior is correct. But comments oftentimes aren't maintained because they don't necessarily need to be maintained as the code is changed. And so you have code drift. You have comment drift. And so the code and the comments start to separate, and then you end up with comments that no longer correctly describe the current code, and then people start getting really confused. And that's, I think, one of the dangers, and I've seen this happen in production quality code dozens of times, maybe more than that, maybe hundreds of times. And I don't think anyone's, I foster goodwill and believe in people. I don't think that anyone is intentionally trying to make things hard. I just think it's easy to sometimes forget that, oh, while we're updating this algorithm and we change this behavior, oh shoot, we got to update this comment because now the description of what the function does is slightly different. Okay, cool. So that piece aside, which I think is actually quite interesting in terms of how we can think about understanding intention from code. And by the way, there's a paper that I think Charles Sutton from Google Brain and August, I think August or Augusta Adena, I think maybe August Adena wrote a few years ago, maybe for, I can't remember what the venue was. But I think it was like NeurIPS or ICML or iClear, ICLR, one of those. And the paper is called property signatures. Really interesting paper in my mind. And almost everything that Charles Sutton does, I think, is I am deeply paying attention to what Dr. Sutton, Professor Sutton, is doing. He's doing a lot of really interesting machine programming things. Somehow he and I don't think we published something together, but he's chaired and co-chaired the MAPS symposium, the machine programming symposium, several times in the past while I was actively running it. Just really incredible guy with tremendous insights into machine programming, machine learning, programming languages, all this stuff. And in their property signatures paper, they make some fascinating observations about the signatures that functions can have and how that information could be used to inform systems, potentially automated systems, about the semantics of the code. So anyway, I'm probably not remembering exactly the right detail of how this works, so advanced apologies, but strongly recommend anyone that is interested in sort of trying to reason about intention or semantics, which are slightly different things, by the way, at least in my mind. Semantics is more of what it means, and intention is more what were they trying to achieve. And in some sense, what you would want in an ideal world is that intention and semantics are the same. What the programmer or the system or whatever was intending is what was actually built, and so the intention and semantics are identical. But as we know from the existence of bugs, that's not always the case, because if it was the case, I think we wouldn't have bugs. Because I don't think any programmer, or maybe hackers and stuff, but normal programmers that are trying to build software, I don't think that it's their intention to create defective software. Defective software, in my mind, and I think Matsson's mind, and maybe Armando's mind, and some of the other co-authors here, I think those defects often manifest due to a mismapping of programmers' intention to what the actual semantics of the software are for the system they end up building. And I've definitely done this myself, right? Like in building Notica and many of the prototype systems, basically per my PhD dissertation, there was some weird data race case where after 10 million transactions, the consistency of the system could have an off by one error. I mean, it was like really crazy in order to even reproduce this type of thing. But this is an example of my intentions were this, but the actual semantics of what I built were slightly different, and therefore there were bugs. So anyway, the other piece about this, which you mentioned, Ahmad, and I think is super fascinating is you were mentioning how we might want programmers to do some sort of labeling or curation, data curation, code curation, where they're kind of like explaining what the code is doing. And I think that that's not a bad intuition. I think that that's one way to do this. But interestingly, I think there are other ways to do this. And some of them they're really advanced and they're very subtle in how you would do it. I don't think I'm quite in the position to explain how one might do this without utilizing programmer annotations, if sort of what I think you were describing. But I will say that there are other ways to do this, and I think that they can be, in some sense, I guess I can strengthen that claim. I know that they can be done, at least in some capacity. I'm not saying that you can necessarily do this exhaustively for all code, but some of the techniques that I discuss at the university in my class, as well as some of the things that we're building at Merle, we do have concrete data that shows we can lift intention. And just to be clear, I'm not talking about semantics here, as we just were discussing. I'm not talking about lifting semantics from the code. I'm talking about lifting the intention from the code, which, as we were just discussing, is subtly different than the semantics, and it is significantly harder because intention is really what the programmer or programmers meant to build, which could be different than the actual semantics of the software. So I guess what I'm trying to say is I am intentionally saying lifting intention in an automated fashion is notably more challenging than lifting semantics. Yet we do have some early evidence that this can be done. And the techniques to do it are wildly advanced. It's quite unlikely that someone that doesn't have a massive amount of sort of sophistication in programming languages, software engineering, machine learning, and then possibly systems would be able to stumble across how this might be done. It requires a deep and nuanced understanding of almost all of the four domains of machine programming. I would say the one that it potentially doesn't require as much would be systems, but that's not totally true in that there are very advanced systems-related things that one can do to discover intention from software, especially when considered from a dynamic execution lens. Now, that might be kind of hard to understand without me explaining what I'm trying to express. But rather than me going down this rabbit hole specifically on how the systems domain can be leveraged to lift intentionality from software, I would recommend possibly taking a look at the AutoPerf paper, which we published at NeurIPS 2018, 2019, something like this, which gives a hint on one way that you can use systems. And what I'm talking about here with systems is actual hardware to discover some aspects of intentionality of software. Okay. I think I've said enough about that, but I really like where you're headed, Ahmad. I'm going to unpause you in a second. But I did want to extend that if you happen to be in NorCal in the wintertime, I think I teach from September to December. I have a seat reserved in my course for you. And the reason why I mention this is your intuitions on some of these things are quite profound. They're very advanced. You're teasing out really interesting ideas, and I think that if you took my course, some of the ideas that you're thinking about would be solidified and sort of explored in a number of different ways that would make some of the ideas that you're toying with much more concrete. So open invitation. Just holler at me if it's something you're interested in.
Yeah. Like it would be amazing if you had a tool where literally, like if you were to open the ClickHouse code base right now, or connect to it, it basically breaks it down in such a way that it doesn't matter if you know C++ or not. It's just really about mapping out the different modules, what they do, and if you want, go into the details of how they do the thing and how it can be improved. Yeah. I mean, a lot of people think that, oh, it's over. Like, Claude Sonnet 3.7 can do this and that. Oh, it's so over. I'm like, gosh, that feels limited, right? Like, there's so much more that we can do for software engineering with these new tools that we're getting, right? In terms of, the intelligence that we have access to now. Like, there's so much things that we can just work on and to advance the field. So yeah.
Yeah, along those lines, I have a similar view. And I was actually just talking with Mattson about this today. He's a multidisciplinary superstar. And so in addition to computer science, I think his PhD is in chemistry, but he teaches physics sometimes. And I mean, he's just all over the place. He's just like the knower of all things. And one of the observations that he's made, which I strongly agree with, is this notion that there's too much code to write, especially as we get heterogeneity in hardware, as is emerging, going back to what Dave Patterson is talking about with the golden era of architecture. So like we have domain-specific languages, now we have domain-specific architectures. And examples of that are specific CPUs that have different domains that they work in, laptops, tablets, mobile, server class, these types of things. And then you have various types of GPUs for laptops or PCs, but lighter weight GPUs that are potentially still discrete, but they're for mobile, GPUs that are meant for things like machine learning or cryptocurrency, different class again. And then you have other things like neural processing units, NMPs, various ASICs, application-specific integrated circuits, FPGAs that can be custom designed with specific layouts for specific problems. That's sort of like hardware that's essentially reconfigurable to be whatever it needs to be. And by the way, huge potential in FPGAs as far as this customization. I think that it's just the challenge of the fast iteration for FPGAs that makes it potentially, I guess maybe there's like two major points of contention with FPGAs. And keep in mind, I'm not an expert with FPGAs, but I have spent quite a bit of time with folks at like Altera when I was at Intel, which is the FPGA company, and also folks at like Xilinx, another FPGA company. So anyway, as they explained it to me, I think there were two fundamental concerns with FPGAs being able to compete with sort of these high-end CPUs. And it was the time that it would take to reconfigure the FPGA for a specific architecture. That's one. And then the second is the actual sort of is like CPI, cycles per instruction, or IPC, instructions per cycle. I think you could use either of them, but the point is that how many instructions can you do per cycle, how many cycles per instruction. And I think that they were saying I'm probably getting this slightly wrong, but it wasn't like a 10x difference, but I think it was close to that in terms of FPGAs being slower. And that's an issue from the lens of if you could reconfigure these things to be specific for these domains, which would potentially mean it would be better than these general purpose systems that don't have the domain expertise, and then they would sort of be more efficient, at least in terms of the architectural layout. But then when it comes to the efficiency in terms of the actual compute, the other systems may be faster. However, one of the upsides is that when you have domain-specific architecture, it oftentimes will be, even if it's slower to handle the compute problem, it will often be more efficient power-wise, because the architecture is now sort of specific for the domain that you're trying to solve something in. Hopefully this makes a little bit of sense. I probably should draw a picture or something and kind of explain this. But anyway, the challenge here is you have all these different heterogeneous hardware architectures that we see today. I mean, it's sort of everywhere. Your mobile phone, it's probably an ARM processor, maybe using Qualcomm Snapdragon, unless you're using an iPhone, and then that's going to probably be ARM, but it'll be Apple Silicon. And then you have your laptops, and this might be Intel or AMD, both of those x86. But then if you have an Apple, if you have a MacBook, this is going to be the ARM M processor, at least these days. And so you can see how this is becoming a heterogeneous conglomeration of stuff. And this doesn't even consider the software side of things, which is also massively heterogeneous. Because we have all these different programming languages that are domain specific as well. Things like SQL or Julia or Python, JavaScript. There's just you name the language, and for the most part, it's going to be specific to the domain. Even languages like C and C++, which you potentially can do all this stuff in, but really they're systems languages. They're meant to be the stuff that things run on top of. And so while you could build your own web app in C or C++, that might not be the best use of your time, because JavaScript and TypeScript are, or even things like PHP, are likely far more strongly positioned for that domain. So from that lens, it's sort of like every language that exists is a domain-specific language. So now you have heterogeneity from the software side, and you have massive heterogeneity from the hardware side, and it's a mix and match type of thing. So who's going to write all the super optimal code for all the various types of hardware? Well, the machines are going to do it. That's who. Because us humans, that's just too many mix and match type things that we need to reason about. But we really do need a high degree of efficiency of the software that runs on this hardware, which essentially breaks down to fully exercising the hardware. It doesn't necessarily mean that we need to peg the CPU to where it's 100% all the time, because that could actually not be, that could be equally as bad, especially if you're oversubscribed and you spend more time caching things in and out and not getting anything done. So this is not what I'm saying. What I am saying is that when you're running a program, you are fully exercising the hardware and the resources that's available to you. This is sort of what I mean about efficiency, is that if you have 8 hardware threads available to you, you can have the system be designed such a way that maybe 6 of those are being utilized by some primary worker program. And maybe the other 2 that aren't being used are used for other things, like monitoring things or oversight for various programs that are going to be switched in and out of context, these types of things. So it's tricky, is what I'm trying to say, is you don't actually oftentimes fully subscribe to the hardware threads. In fact, I think there was something, I'm really going down a rabbit hole here, but I think there was something with the IBM Core processor. This is, I think it was back for the PlayStation 3. And the geniuses at IBM designed this very scalable system that I think it had something like 8 hardware threads. But when you're programming for the PlayStation, it was an unspoken rule that you never used more than 6. And there are multiple reasons for that, but I think one of the key ones is the cache coherence protocol was so relaxed that you would have a really hard time understanding the coherence correctness of the program if you use more than 6 threads. Like, it would be legal for this out of order cache coherence protocol, but it wouldn't make sense to the programmer. That's the first piece. And then the second piece was there was some amount of it was like a lack of determinism in the quality of the processors to where you would be able to reliably use 8 threads on all of the machines. It allowed you the space that if the hardware for some reason didn't have an effective core of one of those 8, that you wouldn't oversubscribe. So you created 8 threads, but really only 6 of them are active due to, I don't know, transient faults or some other like strangeness. So anyway, the point of this is even if you understand the specifications of the hardware, doing the proper mapping from the software to the hardware is probably not nearly as straightforward as it might appear. There, in some of these cases, you actually want to dynamically reconfigure the execution signature for the hardware at runtime to where it's not like something that's set a priori because of the various situations that you might run into. Like you may be running concurrently with this other system that is going to be a very compute heavy or data heavy or something heavy system, and it's going to be running alongside you, and so you're going to narrow your band, because if you don't, you're just going to throttle with this other co-resident process. So this is a very long-winded way of saying that we really need the machines to do a lot of this coding purely so we can work at these higher levels. And it goes back to what you were saying about Cursor and Claude and other things and Sonnet. This idea that somehow programming is over, like, I think that this is a problem that can't be completed. There is no amount of evolution that will ever happen with any kind of advances in compute where humans won't want to create software, or they won't have the need to create software, no matter how advanced our systems are, to do the automation. And the reason for that is software is an enabling mechanism for us to realize ideas that we have in a virtual world. And in the virtual world that exists, there's an infinite number of ideas that we might have. It's not restricted to the physical world. Like, I could almost see that if you had the same thing in the physical world, you might run out of space, so to speak, right? Like, you have so many houses built on all the land that's available on the earth that you no longer have real estate companies, or construction companies, because there's nothing to construct because there's no space. But that's the physical world. The virtual world, we don't have those types of constraints. It's infinite. You know, it's Inception from the movie, the Christopher Nolan movie. It's just a dream within a dream within a dream. It's endless. And so all of these systems, or Merle systems as well, all they're doing is just accelerating our ability to develop software. They're not eliding away the need to create software. In fact, if anything, it's going to increase the demand for software people, because we're going to have more things that we can do, and we're lowering the bar for entry. So essentially, we are making it easier and easier to become software engineers than it's ever been. Is that the AI systems are sort of like helping us with this. And in some ways, I think they may be helping us too much. That we really need to be careful that we don't lose our critical thinking skills, because if that happens, then I think we really are in trouble. So anyway, Ahmad, I 100% agree with you on your view that we're not done. And I would take it even further. I would say that, like I was just trying to describe and probably explain this, pretty poorly, is no amount of advances in software systems will ever elide away the need to create software. It's not a finite space. And truthfully, in order to build the systems to get us to Mars, we need the minutia to be handled by the machine, right? That's what compilers have been doing for decades. compilers have been handling the minutia for us, or even now these runtime engines that do interpretation of scripts at runtime to then do essentially the translation of the higher order script to the machine code that will actually execute on that hardware. That's all the same stuff. It's just that it's not the code that is like directly related to the software we're creating. It's a translation layer that takes the code we're writing and then rewrites it so it runs closer to the hardware so it'll be more effective. All we're doing really is like leveling this up a little bit, so another layer of minutia or complexity is handled by the machine. But again, there are multiple layers of things where the machines are already doing this. Like, I think Java and the .NET framework is a really good example, is that here you have the code, and then that gets translated into this bytecode. That's the machine doing that. And then that bytecode then gets translated to the machine-specific architecture that it runs on, which can be all kinds of different things. That's another layer. So it's a multi-hop system. It's basically compilers sort of on steroids. And so all we're doing here is we're just up-leveling one more time. There is potentially some danger, I think, is that we don't want to lose our ability to think critically. And then on top of that, when the AIs are writing some of this code, by the way, I'm explaining this too quickly. I need to chill out and slow down a little bit. But you got me pretty excited about this, so it's your fault, Ahmad. But what the big fear is that we have to maintain this code. So when you have the lower level systems that are generating the bytecode and they're doing the translation, we never work at that level. And so that's a fully contained black box that does what it needs to do to make the world a better place. We do currently function at the level of programming languages: C, C++, C#, Java, JavaScript, TypeScript, Python, Ruby, you name it, Swift. When the AIs are writing this code, that code is not a one-off. As we know, those of us that write software, we know that writing software code is not a one-off. There's no software system in the world that I've ever seen created that writes the perfect solution to a problem that is evolving over time, which is essentially all software that's being used, and that code never needs to be maintained. That's crazy talk. It just doesn't exist. We're not writing the perfect American novel here. We're writing things like Git and Linux. That's the whole v.xxxxx, because it's going to have iterations as we make it bigger and better and change it and do all this stuff. And so herein lies potentially the problem with the copilots, is that they may appear to be helping us in the short term because they're eliding away our need to do some of this initial code, which makes it feel like we're going faster. But we have to now maintain that code and fix that code, because these systems currently are not very effective at understanding existing code and making it better, fixing the issues that it has, or then adding new features within the context of that existing production quality code. They're very good, though, at doing simple prototypes that are disjoint from a real system. The challenge, of course, is, for real software, not these prototypical toys, is how do we take a system that can do just simple prototypes that have no relationship to real production quality code, and then make those systems work in an iterative fashion on world-class software that is going to iterate over and over, where they deeply understand not just the code that's being written and being maintained, but also the context of the larger system as it stands holistically. So how this is going to interface with these other components. Are we repeating ourselves? All of these things that software engineers, especially our senior ones, are doing today. And so this is, I think, one of the big concerns that I have with some of the code assistants, and why also, I'm kind of in the camp with Linus, is I don't know that we really needed help writing a small amount of code. I mean, sure, it can help us with this, but we could have done that or figured that out on our own. There's decades of evidence that we have, and we do. But I think that we do definitely need help to make the software that is written or that we're writing is extremely high quality. And there's also a ton of data that shows this is a real problem because we perpetually have defects in our code, whether they're logical defects, so they're correctness things, whether they're memory related, so we're crashing, this type of thing, or potentially some of the hardest ones, which are related to performance. And the reason why performance-related issues are the hardest, or one of the hardest, is they're gray. Logical issues tend to be very easy because it's just correct or incorrect, whereas performance issues are windows, where it's what is acceptable performance and what is unacceptable performance, and also how the performance is today may be acceptable, but then as the software evolves and it gets more complex, that same performance may slowly erode and degrade, and now the system that was fully acceptable in terms of its performance yesterday is no longer acceptable today. And on top of that, who decides these rules? Who is the person that's saying, oh, this is not acceptable now? It's very much sort of like this dark art. It's magic in some sense. So anyway, yeah, Cursor and all the coding assistants, they're not solving any of these things. I think it's great that they exist, and I hope that they're helping us in the short term, but also not hurting us in the long term. And truthfully, this is part of what Merli is setting out to do, is to ensure that we actually have fully autonomous AI systems that are, one, helping us with the problems that we cannot handle on our own, which is like assessing millions of lines of code in a very systematic, deterministic way to sort of raise all boats, but then also educating us so we become smarter. Like, this is, I think, one of the superpowers of AI. This is how I use them, is AIs teach me stuff all the time. One of the things I use it for is it helps me identify sci-fi shows that I would like to watch. And I don't know about these things, so the AIs are teaching me about sci-fi shows that I might be really interested in. And they've done it. There's this show, just as sidebar, called Utopia. It was originally a British show from the UK, and then it was remade in the US a couple of years ago, something like that, 2022, maybe 2020, somewhere around here. And I don't know, I watched maybe one episode or half an episode of the UK version. I can't really say whether it's good or not, but from my view, the American version, the US version, is incredible. And this is an example of how I think AIs can be used to help us, is they can teach us things that we don't know about, and they're really good at sort of exploration, this whole creative ideation. and so we should definitely use them in that capacity. We should essentially, my view is we should use them in a way that they provide value on things that would otherwise be nearly impossible for us to do. Like me using the AIs to give me the top 100 sci-fi shows in the last 5 years, this would be almost computationally intractable for me to try to solve. Or maybe I could do it, but I have to dedicate my whole life to it, and I would still not be able to do it with the efficacy that a machine can do it. And so, yeah, let's offload this to the AI. Likewise, also scanning all the code in the world, and not just the current code, but the lifetime of the code, so we can see trends and things. This is also a great problem for the AIs, because this is essentially intractable, or it feels like it's intractable for any reasonable amount of humans. I mean, sure, if you had the entire global population all looking at 10 lines of code on a repo throughout its lifetime, yes, we could collectively probably figure this out. The problem is, last I checked, there's only something like 27 million, maybe 30 million software developers. So even though we're bordering on a global population of 7.8 billion people, only like 1% of that global population even knows how to read code. So yeah, that solution won't work. So offload that to the AI and problems like it, which is a big reason why we're approaching machine programming at Merle from this perspective. Although, admittedly, and this is the last comment I want to make because I'm exhausted, it's almost 3 a.m., and I've got another early day in front of me. But I think the thing I was going to say is, as I think you know, Ahmad, I think some of the systems that exist for software development right now in AI are purely a square peg in a round hole thing. Is that people have looked around, looked at the table and see what's lying around and say, oh, here's transformers. These have incredible value for natural language and soft science. Can't we just make them work for hard science and programming languages? And we kinda, sorta, maybe in a pretend way can, but not really, because they're not really that good at hard science. And so my hope is through the GTT talks and things that you're doing and others, we will help the community realize that those LOMs can be helpful with the stochastic creative ideation, but they can't necessarily be trusted as a source of truth for the very reasons that we discussed about. Is they don't have the logical underpinnings. They don't have the foundation of the house that's required to support all the stuff that's built on top of it. And unless you have that foundational thing, you can't staple on logical systems to it. You can't staple on the plumbing for the house as an afterthought. It has to be built in the infrastructure. Otherwise, it just doesn't work. And so some of these AI companies, I think, are just trying to put it on, and then you get the bad things that T and I have discussed in some prior podcasts. So anyway, that was a very long rant about a whole bunch of things. And so for today, I'm going to wrap this up. But I love the stuff you're doing. I'm going to do more podcasts on looking more closely at the things that you're considering. And I encourage all of our viewers on GTT to dig in on the YouTube channel, Diminishing Skill Issues, and hear the things that Ahmad has to say. I've been paying attention, and while I've only maybe seen 90 minutes of his stuff, I think that he really groks the larger picture of what's going on, what's potentially good, what's potentially bad. And I feel like Ahmad's heart is in the right place, that he's really trying to help us navigate this space to a better future without potentially sabotaging our ability to, like, do science. Yeah. Okay. Thanks, everybody. It's been great.